All right, IBAASL2 kids. We are going to finish off 5.4 today. But first, I kind of want to do one more example with the first and second derivatives and where it's appropriate to use them. So first up, we have this graph right here, or a function, 2x to the fourth minus 4x squared plus 1. First step, we're going to find all turning points and classify them. So remember that turning points are when the derivative is equal to 0, the slope machine. So first step, we'll take the derivative. That's not too bad because those are all power rule. So 8x cubed minus 8x, there's the derivative. Set it equal to 0 to find your horizontal tangents, aka turning points. Now the right-hand side is factorable. They both have an 8x in common. So rather than divide both sides by 8x, which actually eliminates one of your solutions, we're just going to factor that 8x out to the front, and then we get x squared minus 1 left over. X squared minus 1 should set off an alarm bell that is also factorable. Now, you could set both of these parentheses equal to 0 and then, use the square root with a plus minus in front of it. But I kind of prefer just like factoring until I can't factor anymore. So that becomes x minus 1, x plus 1. Then when you set all three of those equal to 0, you get x is equal to 0, positive 1, and negative 1. So these are the turning points, but I don't know which of them are tops of mountains and which ones are bottoms of valleys. So we're going to use the second derivative test. I realize in previous videos we set up like a slope zone test, and then we kind of picked numbers and put them into the derivative to figure out if it was going uphill or downhill. But now that we have the second derivative, you can just plug those numbers into the second derivative. So first up, the second derivative would be 24x squared minus 8. That's just the derivative of the first derivative. And then we're going to plug in these three numbers. So 0, positive 1, negative 1. Put a 0 in there and you get negative 8, which is really, I don't even care about the number. I just care that it's negative. Put a 1 in there and you get 24, 1 squared, take away 8, which is a positive number. And then f double prime of negative 1. Put a negative 1 in there. I believe that's also going to be a positive number. I guess I could write out more of it. Yeah. So what happened? We figured out that, really the second derivative you can think of as a concavity machine. Just like the original function is a slope machine, or is a coordinate machine, the derivative is a slope machine, the second derivative is a concavity machine. So when you get a negative in the second derivative, that means that at this x point, that it is concave down, which means that is the top of a mountain. So x equals 0 is a local max, top of a mountain. Now, when you get a positive out of the second derivative, that means that it is concave up, and that means it's the bottom of a valley. If the concave is facing up, that means that you're at the bottom of a valley. So that means x equals negative 1 and x equals positive 1 are local mins, bottoms of valleys. Find where f of x is increasing and decreasing. So to do that, we do go back to the sign diagram. Do we have to do that? We already kind of know that it's a maximum at 0 and a minimum. So I'm already thinking if you start to sketch a graph, it's like we know that at negative 1, 0, and positive 1, that at the x equals 0, that it's like there's some sort of top of a mountain happening. And then we know at -1, we know there's some sort of valley happening because we figured out 0 was the local max and -1 was the local min. And then at +1, we know there's some sort of valley happening. So I would sort of connect the dots, and I would know that, yeah, it's almost like I'm getting to the last question, which is like sketching the function. I think the book encouraged you guys to do a zone test, to do -1, 0, and +1. And then use the slope machine, which was 8x cubed minus 8x. And then pick points from these zones and plug them in. So test the 4 zones like we've done in the past. But I do think if you plug those in and use the thing that I'm right, that this goes negative in this direction, positive in this one, negative in this direction, and positive in this one. But double check, make sure I'm right. So this means that, gosh, do we have to use the IB notation? Yeah, probably. Okay, so for decreasing, where it's going downhill, that would be this section where it's going off to infinity. And then it happens again in this section from 0 to 1. So that would be negative infinity all the way up to -1, not including it, unionized with the next section, which is 0 to +1, not including. Then for decreasing, or no, that was decreasing, increasing, it's going uphill from -1 to 0, and then it's going uphill again from here to infinity. So increasing would be -1 to 0, unionized with 1 to infinity. There it is. That's your increasing, decreasing. Find the intervals where f of x is concave up, down. Now, because it has to do with concavity, that is second derivative. So I'll scroll up and find my second derivative. It is 24x squared minus 8. So the second derivative tells you where it's going concave up and concave down. And when the second derivative is equal to 0, that's when the concavity switches from concave up to concave down, which is aka an inflection point. So if I set this equal to 0 and then solve it up, we get 8 divided by 24 is equal to x squared. So this is 1/3 is equal to x squared. Then square root that, and we get plus or minus 1 over the square root of 3. Now, I know you're thinking radicals in the denominator, but you know what? IB seems to be okay with it at times. So we are going to do a concavity test. We know that it switches concavity at -1 over root 3 and positive 1 over root 3. So I will pick, or no, I'll put this as -1 over the square root of 3 and this as 1 over the square root of 3. So then we will do a concavity test. Concavity zone test. And we will do that with the second derivative, which is f double prime of x is equal to 24x squared minus 8. Now, I know that, or I'm going to pick numbers that are in zones. So I'll pick a number on this side, which is like, gosh, -1 over square root of 3 is like a decimal that's not quite to -1. So yeah, I'll choose like -1, 0, and positive 1. Those seem like easy ones. So when I plug -1 into here, we get positive. When we plug 0 into it, we get negative. And then when we plug positive 1 into it, we get positive again. Oh no, I'm running out of room. So that means that in the first zone, this is concave up. In the next one, it is concave down. And then concave up on the last one. So the intervals where everything's concave, let's scoot this over, shrink it a little bit. Oh no, come on. Oh, come on. This is great real-time video. Love it. Yeah, we'll just make you real small. This means that it is concave up negative infinity all the way up to -1 over the square root of 3. And then we will unionize that with the other section, which is 1 over the square root of 3 all the way to infinity. And then concave down is going to be just this section right here, which is -1 over the square root of 3, comma 1 over the square root of 3. There it is. Excuse me. Now, we've done all this work to sketch the graph, indicate the maxima and minima. So, we know from all these tests, let's go back and look. We know that it's going to hit, let's use a different color, that these are turning points right here. So we know those are the tops of mountains or bottoms of valleys, and we know which is which because we tested them and figured out this right here, that 0 is the top of a mountain, and -1 and +1 are local mids. Then in the second one, I was supposed to test the concavity, but I almost started sketching it because if you know where the mountains and valleys are, you can start to put them out like that. Yeah, let's go ahead and do it. I mean, you could plug in a bunch of these x values into the OG equation to find the actual coordinates, which I think the book wants you to do, but I'm going to kind of skip that step and show you guys what it looks like. Okay, we know at -1, there's a bottom of a valley, and at +1, there's also the bottom of a valley. We know at 0, there's also a top of a mountain. If you plug 0 into the OG function, this point turns out to be 0, 1. If you plug -1 into the OG function, you get -1, -1, and then if you plug 1 into the OG, it's, they mislabeled that. Sorry, it's 1, -1. So if I was to start to sketch the graph, I know it looks something like this. Also, we found the inflection points. They're right here. They happen at -1 over root 3 and +1 over root 3. That's where the concavity changes. So if I was to look at the concavity, it's like concave up, concave up, concave up, concave up. But then right around here is where it switches to concave down, concave down, concave down. So this point right here is an inflection point. So the purple ones are turning points, but this is an inflection point, which is the point -1 over the square root of 3, 0. And then it happens again over here where it switches from concave down to concave up. And this is 1 over square root of 3, 0 for that point. Okay, guys, I think that's enough for that sketch. Last thing, this is just the graph of f of x. We're going to sketch the graph, well, we already sketched the graph, but we're going to sketch the graph of the first and the second derivatives. You might look at this and be like, what? How on earth do I even do that? I don't even know anything about the equations. So what you got to think of is that the first derivative, it tells you the slope of things. So if you look like in this zone right here, it's going like slope up, but then there's a turning point here. So it's positive slopes in this zone, and then it hits 0. So if I start to draw the first derivative, so we'll say purple equals first derivative, that means that it was above the x-axis in this zone because it was positive, but then it hits 0 at that red dot, the turning point. So that means it's like this. It hit 0 there. So this is f prime of x. Then in this zone, it switches to negative slopes. And then it hits 0 at this point right here. I shouldn't use purple. Gosh, I'm getting wild with the colors, you guys. So that's another turning point. So we know at that turning point, it will cross the x-axis again because that's a derivative of 0. So in between those 2 points, it must turn around. So it's like, it's going to come back and hit at this point. So any local min or local max, like this spot right here, is going to be where the derivative touches the x-axis because that's a derivative of 0. So we know it's going to come back and hit right here. Then at the next turning point, it's going to hit here, and then at the next turning point, it's going to hit here. So it's like every turning point is going to correspond with a 0 on the derivative. So I know it's like going to go and touch here, and then it's going to go and touch here, and then and touch here, and then it becomes negative past that, so something like this. So that's the first derivative. Now, the second derivative, which we'll do in red, the second derivative is 0 when the concavity switches of the original function. So if you look here, it's like in this, there's so many colors. This is all concave up, this is, or sorry, concave down, and this is concave up. So we know the second derivative is going to touch 0 at this inflection point. Now they happen to be the same point there. But we know that the second derivative is negative in this zone because that's concave down, or sorry, positive. No, I'm getting it right. Concave down, it's negative in that zone, and then it's going to be positive in this zone. So we know the second derivative looks something like negative, then inflection point, then it goes positive until the next inflection point. The next inflection point is probably somewhere around here because like this corresponds to the inflection point. So it's going to come back. That's where the second derivative, so we're doing second derivative of x is equal to 0. Then the next inflection point is probably somewhere around here. So we know that's where it's going to come back and hit the x-axis again. Also in between those 2 points, see how this is all concave down? That means negative second derivative. So in between these, it's in the negative zone below the x-axis. Then the next inflection point is here. So it goes concave up, positive above the x-axis, and then it just continues downwards because it's all concave down from there on out. So this way. All right, that putting the derivative and the second derivative on the same graph, I realize it's kind of wacky because it's like, whoa, man, it takes a lot to make your brain think that way. So just to label, the red was second derivative and the purple was first derivative. And it's all, purple is all about what's the slope doing. Red is all about what's the concavity doing.